Okay, I think we can get started. Thank you, everybody, for coming to our Roanoke Valley.net user group meetup today. We meet on the first Thursday of every month. We bring you a great mix of both online and in-person meetups, some months online and some months in person. We have a fantastic presentation lined up for you today. Understanding LLMs, how they function, and how they have changed. And it's presented by Dr. Sebastian Raschka. He's been working on machine learning and AI for more than a decade. Sebastian joined Lightning AI in 2022, where he's a senior staff research engineer focusing on AI and LLM research and development. Prior to that, Sebastian worked at the University of Wisconsin-Madison as an assistant professor in the Department of Statistics, focusing on deep learning and machine learning research. He has strong passion for education and is best known for his books on machine learning and deep learning using open source software. Really appreciate having you here with us today, Sebastian.
Yeah, thanks for the kind invitation. And yeah, I overheard you were mentioning also the PyData conference in Charlottesville. Just briefly, I was there actually 5-6 years ago, and I was supposed to go there in April. Actually, a good friend of mine is organizing that. I can highly recommend it. Unfortunately, I just herniated 2 discs in my back, so I was like taking it easy in terms of traveling. I mean, virtual stuff is okay, but yeah, in person I want to be careful. But I can highly recommend it, to learn about Python and stuff. It's I don't know how many of you are using Python. It's really like the big language in AI and machine learning in a sense. Like, yeah, Python is slow, but the way it's used, it's essentially like a glue around other libraries like CUDA and stuff like that. So it's actually quite relevant again. So yeah, but yeah, thanks for the kind introduction to get started with my talk. So you may notice the title here on the slides is a bit different from the one you just read, Tolga, and that's because there was DeepSeek a few weeks ago, and I think you might all be curious how that connects to LLMs. Like, what does it mean? How is it different from what has been there before? What has changed basically in the last few months, and especially then leading up to DeepSeek? How do you categorize it? What is different about it, and so forth? And yeah, so that's why it's a little bit different. So we have there are 2 main themes. First, like covering a bit about the fundamentals, like what is the general pipeline, how are LLMs developed, and the other one would be it's also intertwined a bit what's new, what has changed, and what's kind of coming with these reasoning models. And yeah, that is interesting because it is a hot topic. You might be already oversaturated because it's everywhere in the news, but my take is usually a bit more scientific, like based on the paper, not the hype. I hope that's so maybe useful. So just briefly about me. So I would say, I mean, I do a lot of things. I'm probably best known at the moment for my build a large language model from scratch book, which is essentially building an LLM from scratch. I think it's one of the best ways to learn really how things work. But the caveat here is it does require like intermediate Python skills because yeah, I wanted to start at some point without giving like a super to make that book basically 300 instead of 2,000 pages. So it's assuming a bit of Python knowledge, but it's really like building something from the ground up to see how it really works. It's like if you're interested in cars, and let's say you work on cars, the best way to learn how a car works is at some point really to build one. Maybe not a Ferrari, but let's say a simpler one like a Model T. It's not like something you would take grocery shopping or even on the highway, but it's it kind of works like a real car. It's just a simpler version of it. So in that sense, it's like the whole journey building an LLM from scratch that can also actually do useful things. It's the same. So the methodologies are the same as the latest LLMs. It's just on a smaller scale. But yeah, that being said, what actually goes into developing large language models? Like, what are the main stages? Of course, we only have roughly an hour, so I won't go into too much detail because it could be, I would say, 2 or 3 weeks, 1 hour, 2 hours each day to cover each detail. But on the big picture level, there are 3 stages. So the classic 3 stages is like stage 1, building. So with building, I mean really implementing the architecture, like setting up the code and the environment and the data set and putting everything together, and then pre-training the model in stage 2. That means then that the model will be able to do soak up knowledge from the pre-training data set and be able to do certain simple things. That was like the first generation of LLMs. And then the 3rd stage is the fine-tuning, or sometimes it's now also called post-training, because there's pre-training and the post-training, what comes after. And that is really, like what made ChatGPT back then, it's I think already 2 or 3 years ago, different from previous LLMs. I mean, LLMs have been around since, I would say, I think 2016, 2017. And ChatGPT in 2022-ish was like a big breakthrough with post-training that you can actually push it a bit further so it can actually follow instructions when you give it instructions. And as you all know, it has just become better over the last few years. And I will tell you a bit also why or what has changed in the last few years. And there is one more thing I wanted to mention here. It's like the specialization. And I think this is something that is already happening. I mean, we have seen that already in 2023, 24, where people develop specialized topic chatbots for medical, legal applications, multimodal LLMs with like LLMs with image support, RAGs for document search. Now it's very popular to talk about agents. Code assistants are already a big thing. So it's not new, but I think this will be also increasingly interesting or focus area in 2025, 26, especially right now, the focus is on reasoning models. I think agents also distilled in cheap models, for example, Apple Intelligence, the smaller models. There's a place for all kinds of things. So previous years was more like focusing on just getting this basic pipeline right. And now it's really, I mean, not everyone needs a general chatbot. It's like, yeah, it's useful, but often you need something more specific, or it's also just wasteful to develop a general chatbot if you can have a more targeted application, basically. So that is actually a big focus area, the specialization. But yeah, because it's only like an hour talk, I will only focus on the reasoning model case in the specialization field here, or in this stage. So yeah, I wanted to briefly talk about these 3 stages. I mean, briefly means probably like 40 minutes, and then talking about the reasoning models. So the first stage, the building, the architecture. So here, really, what I mean with that is, I mean, there are multiple things you would typically do. You would set up the data. There's a lot of filtering that goes into the data set right now, like nowadays compared to a few years ago. There are a lot of refinements in the attention mechanism where you want to squeeze out more performance, or make things a bit faster because it can save you millions of dollars. For example, in DeepSeek, they had multi-head latent attention, just a little tweak there. And yet that, or in Llama models, they use grouped query attention. They're like little tricks people spend time on to optimize things. Then, of course, coding the rest of the architecture. And yeah, and so I have a slide here that shows the original GPT architecture from 2018, and it might look scary if you have never seen it before. There are a lot of little things going on there, and yeah, in this talk, I don't want to go over all these details. This would be something if you're implementing the model. For example, in my book, there's like a whole chapter on implementing each detail, but for this talk, I just wanted to show you a reference how it looked like in 2018, and then the takeaway is actually that things have not changed really over the years. There are tweaks, but it's still the same overall architecture that we are using today when we are using Llama models, DeepSeek models, and so forth. The only difference, if I go back here, is, yeah, there are some tweaks in some of the modules, and the number of times we scale this up here. So this is the blue block. This is repeated a number of times, for example, 16 times, 24 times, 48 times, and that really also has something to do how big your LLM is, because even for the Llama models, you have models ranging from 1 billion parameters to 400 billion parameters, and usually that's controlled by how many times you repeat that block. But there are also other things, how big your vocabulary is, so that determines the size of this input layer here, the token embedding layer, and the output layer. So there's a dependency on the vocabulary size and how often you repeat this, essentially. And yeah, there you can change a few parameters here, how many channels you have in multi-head attention, and so forth. But overall, it's all based on the same architecture. So if you go from the original GPT model in 2018, you can actually go, I did that the other month, you can go through the exercise and introduce all the tweaks that, let's say, Meta did in the Llama model here. At the top, that's Llama 2. Then there's Llama 3, Llama 3.1, and 3.2. And there are little changes. I mean, it's very small here because I don't want you to actually read all of that because it's too much detail, but you can see the form or the structure doesn't really change that much. There are a few things I'm modifying here, but overall, it's still like the same overall architecture. And yeah, so if you are comfortable with Python and PyTorch, I actually have the code on GitHub for that if you want to walk through these changes. And this model also loads the original weights from Meta AI, so you can actually use that. It's not just a toy that doesn't do anything useful. It actually works and gives you the correct text that you would get compared to the official Llama model. Yeah, so just the takeaway here is that not that much has changed over the years, like from 2018 to 2024. I don't have not yet a DeepSeek from scratch implementation. Maybe something I will do maybe next month or something if I have some extra time, because it takes time to do these. But overall, it would look very similar. It's not that much different, essentially.
Sebastian, I have a question.
Yeah.
Yeah. What you're showing with the architecture, the different architecture, is this? I hear the term transformer model.
Yeah.
Is this part of the transformer model? Is this transformer model like a piece of it in here, or is this whole thing all the transformer model?
Good question. So actually, I don't have a slide on that. I could maybe go to show you the paper later. But if I go back to this one, the original transformer paper, the attention is all you need paper, introduced the so-called encoder-decoder architecture, and that was developed for language translation. So you had a sentence, like let's say in German or French, and you were translating it to English. And in that sense, you already had it was like a one-to-one almost mapping in a sense. The encoder, well, it was like another module that was encoding this, and then this encoded input sentence was passed directly into this masked multi-hit attention module, and this one was basically the same. So in short, this is half the original transformer. So people call that transformer-based, a transformer-based LLM, but this is only the decoder part. So there's usually an encoder and a decoder. This is much simpler because, yeah, so the original transformer, it was only for language translation, and this is more general. It's like it has this causal mask. It's generating one word at a time. The original one was mapping the sentence, the original sentence, into a latent representation, passing it in here, and then in addition also generating word by word the translation. It was more basically twice, two of these blocks, similar blocks essentially. And yeah, so but this is not really used anymore. And there was like a model called BERT. It's useful actually for classification if you want to implement a spam classifier and stuff. I have that as bonus material also on GitHub. So like compare this to this architecture for classification tasks. You can actually nowadays actually get almost the same performance with decoders even for classification tasks. So long story short, it is a transformer-based architecture, but it's not exactly the same as the original transformer because it's only the decoder part, if that makes sense.
Got it. Thank you.
Okay, perfect. Yeah, so the takeaway is not that much has changed. It's still, the transformer-based architecture, a few tweaks here and there. There's one thing I wanted to mention, though, that was not on the previous slides because Llama models don't do that. Oh, by the way, I should also say, for example, if you consider DeepSeek, so maybe we'll get to that later, but there are multiple DeepSeek models. There is the R1 model, and R1 comes in like R1.0 and R1, and there's also R1 distilled, and the distilled models are fine-tuned versions of Llama and Gwen. So one of the DeepSeek models is actually based on this Llama architecture, essentially. So exactly using that model and then further fine-tuning it. The only difference is they use the 7 or 8 billion and 70 billion versions, but the architecture is the same between the sizes. The only difference is how many times this block is repeated, essentially. Yeah. So yeah, the takeaway is really not that much has changed. There's one more thing I wanted to mention is mixture of experts. And I think you've probably heard about this term when you were reading about DeepSeek. So what does mixture of experts mean? So there was, so they didn't invent that, but there's a company called Mistral AI in the EU. I think they're in Paris, and they had a pretty good model last year in January. And that was using the mixture of experts. I just use that model here because that was pretty popular back then. And this is very similar to the Llama architecture, except that they, in the feed-forward part, so it's like a essentially like a matrix multiplication, a linear layer. They replaced that one with 8 layers. So that makes the model a lot larger. So if that is about, let's say, 8 billion, if you have 8 of these modules, the model size is about 47 billion. So it's actually, they're quite large. These they look like very small here in the architecture, but they get repeated n times, and they are really quite large. So you make the model much bigger by just having these feed-forward modules duplicated, or not duplicated, but you have multiple of those. And yeah, as you know, the bigger the model, the more expensive it is usually to run and to train. But the trick here is that we don't use all the experts at the same time. So there's like a router module, and in this case, it targets 2 experts at a time. So instead of using all of them, all 8 of them, we're actually only using 2. And in this case, the whole model has 47 billion parameters, but we only use 13 billion at a time. So why do they do that? It's essentially, it allows the model to still have a lot of parameters to learn from the training data. But then when you use the model in inference, which means essentially during prediction time, when customer use it, you save a lot of money because you don't actually use all the parameters. You only need, or you only use those that are currently needed. And what's needed is learned or decided by the router, basically. And yeah, I mean, they are called experts, but they don't really specialize into concrete categories. One might say, oh, this one is, the first one is maybe focused on finance questions. This is the 8th one is maybe focused on medical questions, but it's not so clear cut. It's somewhere in the latent space. It's like a very soft boundary between these topics, for example. So there's not like a specific thing where you can say, oh, this expert learns that. But conceptually, you can think of it as for certain questions, you don't need all the parameters. In this sense, the router can effectively route to the module that is most useful for the given user query, basically. So basically saving parameters. And the reason why I'm mentioning that is DeepSeek is also using that, except their model is much larger, and they have 256 of these feed-forward modules, and they use 8 at a time. So even though their model is 671 billion parameters, the flagship model, they are actually only using 37 billion at a time, which makes it also relatively cheap. I mean, it's still very expensive, but it's not as expensive as running a Llama 400 billion model, for example, which doesn't have this mixture of experts. The downside is it adds complexity. When you're training or developing that model, it is a bit more complicated in code to implement that and also to train these effectively with the raw term. So it's like, yeah, if you want to develop a simpler LLM, yeah, you don't use that. So for example, Llama, they didn't do that, and many people actually don't do that because this is only an advantage if you really deploy an LLM at scale. So if you have millions of customers, then of course it makes a huge difference if you can save a few cents on each customer, basically. Yeah, okay. So I was briefly introducing the architectures, but I'm also just coming back to the model sizes, how they have changed over the years. So there's, for example, I mean, there's of course an infinite number of LLMs. I'm showing you some here. So there's GPT-2 in 2019, and back then LLMs were relatively small. I mean, 124 million to 1.5 billion parameters. And I try to draw them here as circles and then make those proportional to these parameter sizes. So what I'm trying to say is in these 4 years, LLMs became a lot bigger. So we have now 7 billion to 65 billion. And then there was another Llama model in 2023. Things seem to stay constant. Okay, 70 billion is maybe already pretty good. The model got better for other reasons, data set mainly, and refinements to the training procedure. But the size, they kept it the same, except then in 2024, they expanded the sizes in both directions. So there is now, for example, a 1 billion parameter model. Why is that interesting? I mean, right now it's also a lot of, LLM or interest comes in terms of private LLMs. So we, there's ChatGPT, but not everyone can use ChatGPT because first you need internet, and second, maybe you don't want to post all your private queries or data into ChatGPT, for example. And I'm saying ChatGPT, but there are of course also other providers, Anthropic, Google Gemini. I mean, just as a placeholder, I'm saying ChatGPT, but yeah, of course, I mean all the other ones as well. And so, for example, Apple has their own LLMs on the phone. They're not very good. I mean, based on what I've heard, my phone is too old, but based on what I've heard, they're not great. But it is something I think that people will keep working on. So there are smaller LLMs that you can deploy on devices, also not just the phone, but also your laptop, for example. And then on the other hand, there are more capable LLMs, the bigger ones, 405 billion, which are very expensive. So for this one, for 405 billion here, you would need technically, I think, at least 8 A100 GPUs or H100s. And that would cost about like $20, $30 an hour. And just running this for a workday, 10 hours, you would pay $300 just running the server, basically. So yeah, depends on what you want to do with the LLMs, right? But yeah, developing it is actually like
You're making me feel better about my ChatGPT Pro subscription, Sebastian. $200 a month is just ridiculous.
Yeah.
But if you not all of a sudden when you talk about what you just said.
And so this is a 300 a day, sorry, not a month. And so it's $30 an hour, basically. So it's quite, yeah. I mean, if you are a big company and you use it a lot for all your employees, for example, it might make sense. But yeah, I think most people don't want to deploy their own LLM because it's quite expensive. I mean, in that context, the ChatGPT subscription is actually not that bad, or using the API, for example. Yeah. And a few more. So there's Gwen 2.5. I'm just having it on here because it's actually a really good model. It's considered one of the best models. Not last year, but the year before, I was part of organizing at Europe's the LLM Efficiency Challenge, and it was a competition where people were trying to train the best LLM on one GPU in one day. So they had half a year to do that, but the restriction was the winning solution has to train in 1 hour, like fine tuning and stuff. Sorry, 1 day on one GPU, and most of the winning solutions were actually Gwen-based. Back then, it was a previous generation of Gwen models, but they are really good models. It's just they work very well. They're very competitive, and DeepSeek also has some models distilled based on Gwen and Llama, basically. And then, yeah, of course, there's DeepSeek with 671 billion parameters, so big model. But as I mentioned before, they're using mixture of experts approaches. So in that sense, the model is actually smaller than that. So the number of parameters you actually end up using. So this is what you have to have in GPU memory, but you're not on a query. You're not using all the parameters at the same time. So it makes it look a bit bigger than Llama, but actually Llama is the more expensive model to run, which is a bit counterintuitive if you just look at the numbers. Yeah. So yeah, then just a little bit about pre-training. So this was like a lot of architecture stuff, and just a little bit about pre-training. So there are a lot of course, details, and in this talk, I want to talk about like model evaluation and these types of things. But if there are questions, I can happily also share some information on that. But yeah, what goes usually into the pre-training is not super complicated. If you have done like machine learning or deep learning before, it's essentially the same. Even the same code I would use for training a convolutional neural network, for example, for image classification. The only difference is the data set and that it is at a much larger scale. So just to take a step back to explain how the fields are related, this might be something you have, we probably already know that AI is like the superset or the big field surrounding machine learning and everything. But I think especially like in the last 2 or 3 years, the way AI is used, the word, it sounds like it's something very specific to, image generation or LLMs or something. But this field has been around for like close to 80 years. And it used to be just like the field focused on implementing or automating things with decision making. So coming up with algorithms or rules to implement decision making. So with that, I mean, you can think even of video games back, when I was a kid in the 90s, I played video games and it had AI and there were no LLMs back then. And so you can actually implement AI just with simple if and else statements. You don't need machine learning or anything. It's clever if and else statements and you can implement AI. It's just a lot of work. So people 1950 or something started the field of machine learning, which is essentially learning from data. So instead of having a human come up with the rules, it's essentially about algorithms that can learn the rules from the data. So an example would be email spam classification. So what you could do is you could technically, to implement a spam classifier, you could look at a lot of emails and then, if the subject line contains, I don't know, sale or something like that, it's likely spam. And you can think about a lot of rules and come up with a lot of filtering rules to find out what is probably spam, but it's a lot of work, and you have to test it. It's pretty labor intensive, especially if you want to also do that for other tasks. So what you can do is you can actually label a few emails. You can move them to your spam folder, and then you have an algorithm that tries to find patterns, like what makes the spam email different from other emails, like on a data set of 100,000 emails. And in this sense, you automate this process, and that would be machine learning. And yeah, deep learning is machine learning with deep neural networks. It's essentially training a model that has many layers of matrix multiplications, and it's like a special, like a subcategory of machine learning, a special case of machine learning. There are multi-layer perceptrons, convolutional networks, recurrent neural networks, and the transformer architecture, for example. And large language models are again a subcategory of deep learning, and they are basically based on a transformer architecture nowadays. But there are also other architectures like Mamba, like state space models, and so forth. And I just wanted to show you the relationship between AI, machine learning, deep learning, and large language models. And that being said, actually the way we train large language models is a pretty standard deep learning training loop. So it's the same loss function, the same algorithm that I would use to train convolutional network to classify images, for example. The difference is really the data set and where we get the labels from, and that large language models are typically much larger than other types of neural networks. So for the data set, how it would look like, I mean, this is a very small example, so it fits on the slide. But if we have a text sample here, how we would construct the data set is we would slide over the data set, moving it like if this is the size of 4. 4 is only here so that it can fit into one slide, but usually it's something like 2048 or 4092 or something like that, like much larger. It's actually as large as you can make it, because then you utilize your GPUs better. But in this case, I'm keeping it to 4 words in one row to keep it small. And you would just slide over the data set like that to create this input data. And the target data, it's a bit hard to, I would say, come up with a figure that captures that. But what I'm trying to show here is it's the input data shifted by one position. So the model learns to predict always the next word, if that makes sense. So basically, if the model is given this blue thing here, it, for example, learns in the heart of, the next word would be the, it predicts the, and so forth. So you always have like the next word in the next row, for example. So it's like shifted by one position. That's essentially what LLMs learn during training. And what's really nice about it is that you don't have to label anything. Like in classic deep learning, if you want to classify images like cats and dog images, what you have to do is you have to look at all these images and write down the labels. Okay, this is a dog, this is a cat, this is a dog, this is a cat. And then the algorithm can learn from that. In here, we don't have to do anything because the label is always the next word that the LLM predicts, basically. So you can create that automatically. And that allows people to train LLMs on 15 trillion tokens, for example. A token is about a word. Usually a word is like 2 to 3 tokens, but let's say if it's a 1-to-1 ratio, you can think of it as 15 trillion words nowadays. Like DeepSeek was trained on 15 trillion words. It might be around 10 to 20 terabytes of data, basically. And you don't have to label anything, which makes this work at scale, basically. Now, usually we train for 1 to 2 epochs, which means 1 to 2 iterations over the dataset. Because the datasets are so large, usually you only do 1 iteration over the dataset, because it would already take months, like 2 or 3 months. And in the case of DeepSeek, cost $6 million. And in the case of Llama 3, I think they paid almost $80 million. So it's quite expensive. People would run this longer, but it's just prohibitively expensive. They would usually also get diminishing returns. Here, it's on a very small dataset, just to illustrate it. On a bigger data set, it doesn't look so extreme. What I'm trying to show here, though, is the training loss improves, which means that the model learns from the training data. It learns to memorize the data, basically. It becomes better at predicting the next word, basically. But if you give it new text that it hasn't seen before and it tries to predict the next word, you can see at some point it's plateauing, it's not getting better. So if you get this fork here, basically, the bigger the fork, the more the LLM just memorizes. And that's also not good. So actually you don't want to train it too long, because then the model will always regenerate what it has seen in the training data. And then the LLM has a hard time doing anything useful, because it's regurgitating what it has seen in the training set. Yeah. I mean, they will, of course, to some extent memorize anyway, but you don't want to over-memorize, basically. I mentioned it's a pretty standard deep learning training loop. So it's the same I mentioned that we did 5 years ago, 6 years ago. There's a different stuff. Back then, for example, in 2018, I could do everything on my workstation. I had a workstation with 4 GPUs on my desk. I could just train all the models for my research there. And not all the models, but I could do a lot on that workstation. Nowadays, on a workstation, you can do, you can't really do anything except running your LLM, but you can't really train it. So nowadays you actually need a data center for that. So it's a bit sad, but yeah, I think that is where we are right now with LLMs, that they are so big it costs millions of dollars, and you need a whole data center for that. The good news is you actually don't have to train LLMs, because a lot of companies share weights openly. I mean, DeepSeek, Llama, they all have open weights. So if you want to use the LLM locally, you can download those and actually use them without having to spend the money. But yeah, so nowadays, basically how I train LLMs, when I do that for research purposes, I get access to cloud compute, and actually I just do everything on my laptop, SSH into the server, and run things there. Basically, that's how things have changed in the last few years. I have a little, audience question, but yeah, go ahead before we go to my question.
Oh, sorry. When you were talking about the training earlier on, you said there was a competition to see if you can train in an hour. Were we talk about the pre-training for that? We do it for an hour, or
the pre-training for an hour? I said. So this was just running the LLM. Sorry, this is when the model is already trained and you are using the model. Then you pay basically $30 per hour. That's what I got.
Okay.
Yeah. So that is you just using the model. So that for the Llama 400 billion, when I ran it, I could run it on 8 GPUs, 8 A100s. But if you train a Llama model or the DeepSeek model, you use usually, I think for Llama 3, they use 16,000 GPUs. So that's, much more than, it's 2,000 times the 8 GPUs. And then this is exactly the point I wanted to get at. It adds a lot of complexity, because then you can't run it on a single server anymore. You need actually multiple nodes, multiple servers, and they have to talk to each other, basically. And that is where things get really complicated. So there are 2 other aspects of, maybe also from the audience. So I can just briefly stand up. My back is okay, no worries, but yeah, sitting is sometimes a bit hard. But just like a little icebreaker, like a question to the audience: what do you think are other challenges? Why is training LLMs so hard compared to other types of models, besides the cost, for example?
Yeah, I was actually going to suggest that it's the sheer amount of processing power that's needed, but that's kind of the cost, right?
Yeah, I think it's almost maybe then a trick question, but that is kind of like what I was trying to get at. It's like it's the cost, but so like you said, the processing power, but then related to the processing power, what is quite hard is really, first being able to afford the processing power. But even if you have money, let's say you are a finance company and you have a lot of money, or your bank or something like that, even then it's not super easy to train LLMs, because GPUs right now are in such high demand that you can't just even get hundreds or thousands of GPUs on the cloud, even, because because they are so high in demand that you can't just get it right now. A lot of companies want more GPUs, and yeah, and there's a question from the audience, an answer, I mean.
Sorry, this is more of a question, but it seems like, you needed a big data center to run some of the early models years ago, and then computing power increased on the desktop computer, and it became affordable to everybody. And so there's this huge explosion in the availability of machine learning, et cetera. But now it seems like we're going back to, you have to have special, very expensive resources in order to move forward. Would you think that's, what's your thoughts on that statement?
This is exactly right. So I remember it was like 2018 or something. I was at a conference and I gave a talk, and there was some person coming up to me and mentioned, hey, I was using, might have been 2020, 2018, something around that time. I was doing a lot of Bitcoin mining, so I have all these GPUs. Can I actually use that for deep learning, basically? And I said, well, what types of GPUs? And they had, the person had AMD GPUs, and that is a bit tricky. So a lot of the stack, the deep learning stack, is optimized for especially NVIDIA GPUs because of the CUDA drivers. And it's like for historic reasons. I remember when I was a student back in 2011, we did molecular dynamics simulations, and NVIDIA sent us actually GPUs back then, and we had to do the CUDA stuff manually. Actually, I never really learned CUDA, but my colleague actually did, my desk colleague. But we were running molecular dynamics simulations back then on NVIDIA cards, and I think that's where they had a head start in science, where there are a lot of scientists using the GPUs besides the gaming community. And and I think they learned a lot from these lessons, the early lessons, and that's why they have such a head start. And like you said, still, okay, people have GPUs. It needs to be almost the right kind of GPU. You need to have a lot of them. And also it matters a lot what type of NVIDIA GPU. For example, the V100, which is, I would say, 5-6 years old, it didn't have these tensor cores. And it sounds like a little thing, but they have like optimizations. They almost make your GPU on a right data type, float 16, run twice as fast with tensor cores compared to no tensor cores. I mean, a GPU without tensor cores can run float 16, but they have some optimization specifically for that. And so in that sense, the newer GPUs also have a big advantage. So it's like having the GPUs, but almost like GPUs from 4 years ago are almost useless nowadays. They're too slow. They are still expensive in terms of electricity. But yeah, it's like a race where people just try to get their hands on GPUs. They get their hands on them, and then they're outdated and they try to buy the next ones. And I don't want to speculate about stock market stuff, but the price of NVIDIA usually keeps going up, and because it's such a high demand, and they are like the main player at the moment. I do think we will hopefully see other companies catching up. AMD, they always try to do that. They have, I think I don't know how it's pronounced, maybe ROCM. It's ROCM. And they have something that is similar to CUDA, but it's not quite as mature. You can use it for deep learning, but yeah, I don't know, it's not quite there yet. It's like buggy, I would say. So getting access to the GPUs, but then also really managing them. I mean, even if you are a big company, you can afford cloud GPUs. It's not super easy still to run the pre-training. So I wanted to show you some things from the Llama paper, for example. But before we get there, for example, this is from the DeepSeek paper. They spent 2,600K, so it would be 2.6 million GPU hours, and they assuming that one GPU is $2 per hour, and that is also pretty good estimate. So for a normal customer, you would probably pay even $5. They maybe have a contract where when you have a contract large scale, you get it cheaper. But it's actually a pretty good price for an individual if you would go to AWS. So AWS doesn't have HA100s, they're only for the Chinese market, but HA100s would be the equivalent, and I think they're like $5 an hour or something, at least. And so they paid $5 million, and if you probably heard about in the news, it's actually considered cheap. So Llama was like about 10 times that, because they had a lot of computational tricks. But the one more interesting thing here is also, you can see that the bulk is spent on pre-training. Only a relatively small amount is spent on post-training. And this is for a large 670 billion parameter model. So you can, so the good news is you can actually do a lot of exciting work in research, or as a hobbyist, you can actually do a lot of fine-tuning and stuff like that in a more affordable way. So with 8 GPUs, you can actually do a lot also. Maybe not with a 600 billion model, but with a 70 billion model, for example. And here, I mean, this is $10,000, right? But this is for the big model, and for a small model, you can do it for, I don't know, $50, a few $100, like interesting research already. So there is also the silver lining, because you can download pre-trained weights and just skip the pre-training and just go to the post-training, basically, which is nice. Otherwise, it would be very depressing to work in or with LLMs if you see these sticker prices here, basically. Yeah, so here, I don't know how accurate this is. I found this online on a website, because the official numbers were never shared, how much money they spend. It's just an estimate. But I think this might be pretty accurate if you look at how many hours they used, so in previous models and so forth. So they had, that was in the paper, I think, 16,000 GPUs. And I don't know if this number was in the paper, 30 million hours. But yeah, so they spent still, according to rumors, much more than DeepSeek. So DeepSeek, the 5 million is actually quite cheap because they were pretty efficient with their algorithms, basically. Yeah, a few more things, though. I mentioned the managing is hard, so managing the compute resources. So this is from the Llama paper. A lot of issues come from the fact that you have outages. For example, this model was trained for many months, like 3 months or something. And if you look at a 1.5 months snapshot, they had 466 interruptions, and 78% were due to likely hardware issues or GPU issues. So even if you have these GPUs, and let's say you train it on the cloud, there are always like GPUs failing. I mean, if you have 16,000 GPUs, you use them 24/7, they get hot, they might fail, hardware might fail. And this can be very expensive. So you have to always snapshot your model, like save checkpoints. And these are very large. It's like 500 gigabytes, terabytes. And it takes also time. And so you have to kind of manage all of that. And if something gets interrupted, someone has to restart that. And it's essentially a whole team effort. It's like back in the day, a single person could do these things. But now you need I don't know, at least 10, 20 people, like engineers, watching it constantly, managing it and stuff. So it's actually training an LLM is actually quite the undertaking. But like I said, you can actually do quite cool work with host training, which I will get to later. And yeah, the increasing price and complexity is one aspect why it's getting more expensive, is the models are getting larger, but also the data sets are getting larger. And then on top of that, it's the training is getting a bit more sophisticated. So I have, I think, a slide on that later, where people do try more things, like where it's multiple stages compared to a single stage now. But yeah, just again, like the model sizes over the years, things are getting bigger. The same is true for the data sets. So here is a similar chart, but now it's for the data set. So back then they trained GPT-2 on 40 billion tokens. And then, yeah, it got bigger, 1.4 trillion, 2 trillion. And the latest Llama model was trained on 15 trillion. And DeepSeek, for example, was also trained about on 14 point something trillion. So it's yeah, much larger data set, which of course is also more expensive. So you need more GPUs to iterate through it. What's new on the data set side is in the last year, we have, especially in the last 2 years, if you, I mean, my information is only based on what's published, the papers. They added a lot of data filtering, so to remove low quality data. In the beginning, it was a lot about just quantity, like just let's make the data set as much as possible, download everything from the internet and books and everything. And now it's a bit more, I would say, sophisticated. So they're also using LLMs basically to filter out identify and filter out low quality data. So it's getting more sophisticated. Also the data mixing, which means making sure the data set has math, code, and all of that already included. So like having a mix of different things, especially if you develop the foundation model, the base model. There's also now a lot of data synthesis where other LLMs are used, like GPT-4, ChatGPT, to generate additional data and to improve data. Including instruction data already during the pre-training. For example, Gwen and Apple did that in their papers. And then multiple stages where a lot of people nowadays also use LLMs to query large documents. So like pasting a document into ChatGPT and asking like, oh, can you summarize that? Or can you answer a question based on some information that is in a very long document? So the long context, the long document tuning is also a particular stage nowadays in the pre-training to make sure the LLM is pretty good at recovering information from long documents, because in the older LLMs, they were pretty bad at that task. So there were studies showing basically if you have information early in the document, it is more likely that LLM gets the correct information compared to the middle of the document. Nowadays, they're more robust to that. And yeah, nowadays also they save the highest quality data for last. It's just some refinement there. Actually, I summarized this earlier this year from a few papers like Llama 3, Gwen 2, Apple Foundation Models, and Google's Llama, and from the papers like what they do exactly. So you can see not everyone is doing all the things. It really depends. And Llama 2 is a really good model, but they're not even doing all the things, and still it's a very good model. It's a good model for other reasons. They have a very big vocabulary, for example. But yeah, so there are lots of things that have changed, let's say, in the last few years. If you want to read about this, I have actually also an article where I go through this a bit in more detail. But yeah, this was just an overview of the pre-training. And yeah, the question would be, should you actually pre-train a model? Just to maybe one answer to see, yeah, if what do you think? I'm curious, basically, if after what I told you, should you pre-train models if you work with LLMs?
I mean, could be even if you wanted to.
Yeah, that is true. But yeah, I think even if you have if you are a company and you're considering training your own LLMs because you want to develop a chatbot or something for the customer support or something, I wouldn't bother with pre-training. I think it's important to understand pre-training, makes you also appreciate all the open weight models. But honestly, I wouldn't almost say waste money on pre-training. We are fortunate that other companies still share the open weight models. It might not be forever, but as long as you can download Llama models and let's say DeepSeek locally or other models, I mean, I would not spend money on pre-training, to be honest. I would just focus on the target application, the specialization, basically.
So DeepSeek did it in $5 million, right? They did their training in $5 million. But what's like if you took one of the smaller models, what's a reasonable model you could do? A smaller model, what would the cost be? Like, could you get away with doing one for 100 grand?
Yeah, that's a very good question. I did this math for Llama 2 because they had the exact hours. I did this like last year, and I maybe can find it. I posted this on LinkedIn or X, Twitter back then, where I had the table, and I did actually a very similar calculation to this one here based on the numbers of Llama 2, and they had, I think it was for the 7 billion model, and I think it was about 300, 400,000, but I might be wrong here. I would have to look this up. Maybe I can find it later, and I can just redo the calculation. But I think you're about right there, a few $100,000. Yeah, sounds reasonable. But also the price has gone down. So back then, GPT-2, I guess, was also a few $100,000, maybe $1 million. Nowadays, you can train it for a few $1,000s, basically, on the same data set size. So because the GPUs are so much more efficient also nowadays. Yeah. But yeah, so for educational purposes, I would say for research and educational purposes, it's a good exercise to pre-train an LLM just to see how it works. But for practical reasons, I wouldn't spend money on that. So in my book, for example, I'm just training it on one public domain book from Project Gutenberg just to show how it would work. And then I have like an optional material where you train on the whole public domain books from Project Gutenberg. It takes about a week. So in the book, you can do it on a laptop in 20 minutes, just for, it's the same algorithm just to see how it looks like. In the bottom material, you could, on one GPU, train it in a week on Project Gutenberg. But, it's more for educational purposes. I would not spend money on it, basically, as a company like investing into this, basically. Yeah, it's also the other thing about it is these models get outdated so fast. I mean, I showed you there was even 2 Llama models in 2023. It's like you develop this model, invest millions of dollars, and then someone else has a better model that is out in like 2 months, and yeah, so then your model is worth nothing because the other model is already so much better, yeah. So I mean, we are fortunate people are sharing their open weight models. Might not be, like I said, forever, but as long as that is happening, I think just using existing LLMs, and you can use actually the smaller models on your laptop. For example, there's an open source. I don't know if I think it's open source. It's called Llama. I worked on a library called LibGPT. Also, I mean, there are multiple ones where you can run an open weight LLM locally. You don't have to write any code. It's just a few commands. And as a user or a small company, if you just want the private LLM, you can run it locally without having to pre-train your own LLM. So what's more interesting, also as a researcher to me, is essentially the post-training. That is also where, yeah, I would say you see the biggest gain where you differentiate the model for your specific use case, basically. So yeah, just to talk a bit about fine-tuning and post-training. I know it's already, I think, 1 hour. A few slides left. I don't know how long the meetings are usually. I have maybe 20 minutes left, but yeah, and maybe questions.
That sounds about right. We usually finish between 7:30 and 8.
Oh, okay. So yeah, we talked about pre-training and then fine-tuning, post-training. So fine-tuning is how it was usually called. Nowadays, the term post-training seems more popular, but it's there's a lot of jargon in the field. It's basically the same. Yeah, and so there are multiple things you can do here. A classic example would be training a classification model. So you could, like if you have a database and you want to categorize documents, you can actually train the LLM just to classify things. And this is much easier. You need much less data, and you can do that with GPT-2 in 2 minutes. So I actually trained a spam classifier, a GPT-2, the smallest model, 120 million parameters, and on a laptop, MacBook Air, it was like 5 minutes, not 5 minutes, but maybe 10 minutes, and it got like 92% accuracy, basically. So you can actually do cool things with small LLMs. This is for educational purposes, but you can now imagine scaling it up a bit. And so it's kind of like, you don't need maybe LLMs for that. You can have a naive base classifier, but LLMs are actually quite good classifiers, especially if you have unstructured text, basically, like customer emails. You can categorize them and all kinds of things. But what's more interesting is the personal assistant application, and that is basically ChatGPT. Like, where you have something that can do a lot of things. You can ask it, hey, summarize my text, or translate my text, or tell me who was the first, I don't know, person on the moon, or something like that. So you can ask it questions, and most of the time it's right. It's not guaranteed, but depending on the question. But it is actually more like what I'm trying to get at is it's a more general purpose type of model. It can answer and ask free-form questions. And so this process is usually called instruction fine-tuning, because you fine-tune the model on instructions. And when you read literature, it's usually called also supervised fine-tuning, or SFT. It's like SFT is like almost more popular than supervised fine-tuning now. It's like LLMs and large language models. Almost no one says large language models anymore. They just say LLM, basically. And how it works is you have a data set. So here, for example, in JSON format with an instruction, for example, classify this as spam or not spam. Then you have a text message, and the output could be spam. Could be a sentence, this is spam, something like that. So you have a different example. Rewrite the sentence using passive voice, and then the team achieved great results, and the output would be great results were achieved by the team. Now, the thing is here, if I go back one, so there's less information. The thing here is you have to create this data set, though. In pre-training, you can just use unlabeled text, but now you have to create this data set. You have to provide the correct answer. There are actually LLMs. Also, I have some code on that on GitHub. You can use other LLMs like ChatGPT or Llama to generate such a data set. But let's say it's a chicken and egg problem. Before LLMs were a thing, you had to actually come up, or someone had to come up with these data sets, basically, to train the first generation of LLMs. So, and what you do is you collect this data set. Usually, I mean, back then, the first one, Alpaca, was about 50,000, but you can already, get good results with 1,000 of these examples, instructions. It depends really what your target application is. If you want this model to be more, I would say, general, more capable, the more the better. Usually, I would say 50, 100,000 of these examples, and then you format it in a way that is more intuitive to the LLM. So you don't usually give it JSON. You format it as human written text, and here it looks still not like human written text. It has this instruction field, an input field, response field, but this is just a template. So this happens behind the scenes. You as the user, you would only, let's say, write the instruction and maybe the input, and then the formatting is applied behind the scenes. So you wouldn't even, later on when you use ChatGPT, you don't see these types of things. And when the LLM responds, you don't see the hashtags respond, because you can strip that out programmatically, with regular expressions, for example. And there are different templates. This is just the Alpaca style, the original, but there are other ones that are, similar, simpler actually nowadays. You don't even, most of the time, use these special tags anymore. But so you pass on this data now to the LLM for training, and the training itself is the same as the pre-training. The difference is really only that you have now the response here. Before it was just unstructured text, now you have some more structure. And then once the LLM is trained, let's say when you use ChatGPT, you only provide this gray part, and then the LLM comes up with a response. And you can programmatically then strip out this response line. Basically, you wouldn't need to show it to the user even. So it's only during training. And it's, like I said before, it's still a next word prediction task. So what you do is you slide over the input, create this data set. So this is for the pre-training. It's the same slide I showed you earlier. The only difference now is that for a given input, you don't chunk it. Before, you had these chunks where you just take chunks from the input. Here, it's size 4. In reality, it's a bit bigger. It's 4,000 something. Usually, you can, it depends on what GPUs you have. But here, you make sure that one row is exactly one example, basically. And that is just to keep them independent, basically, each as an independent example. Where here, you don't have that restriction, because the model learns just to generate text. And if you actually use LLM that has not been fine-tuned, especially the earlier generation ones, you will see it will generate infinite text. It will never stop generating text unless you cut it off, basically. Because they've never learned how to stop, basically. They're just, continuing. And here, how you do it, how you get the LLM to stop is when you create the target data, it's still sliding it over by one position, but you end with the end of text token. And then on the API layer, you can say, if you encounter this end of text token, stop generating. You just cut it off there, basically. And so you still have this one to shift by one position. So the algorithm is exactly the same. So actually, also in my book, for example, in one chapter, we are pre-training the LLM, and then I'm not even redefining the function. I'm using the same function to instruction fine-tune the LLM. It's the same algorithm. It's just how the data is formatted, what's different, basically. Yeah, I maybe can answer this to get to the last part. So why it's called supervised fine-tuning is essentially because we have human supervision where someone has to write the data set, the outputs in the first place. Yeah, there's one more step though to the post-training. I hope that's not too boring here, but this is basically the magic in ChatGPT, why it's also getting better and everything. It's this preference tuning, and it's essentially tuning it to the preferences of the user. So, for example, if you have a query that is, what are the key features to look for when purchasing a new laptop? If I would ask you, everyone would give me probably a different answer. And I bet every answer is a pretty good answer, but they're all different. So there's no, I would say, there are probably incorrect answers. If someone would say, I don't know, something, you can say probably something crazy, but what I'm trying to say is there are multiple correct answers. So there could be a technical response. So when purchasing a new laptop, you could focus on, RAM, SSD, storage size, and stuff like that. Or we could give a more general user-friendly response to a non-technical audience. So like when looking for a new laptop, we can think about how it fits into our daily life, choose a lightweight model, and they're not, wrong. They're just two different answers. And so, yeah, and so the trick is essentially in preference tuning, you get the LLM to prefer one answer over the other without telling it, okay, this is wrong. It's just like, I prefer this answer. And this is how you customize LLMs for different audiences. ChatGPT is very general. So in that sense, they don't necessarily do it on that level. But what they preference tune is, for example, they minimize the number of swear words, for example, or that the LLM doesn't share sensitive information, basically. So, so in that sense, if someone asks, let's say, how to build a bomb or something, there could be the instruction. Maybe it wasn't a training set, but you can also have an answer where it says, sorry, this is a request I can't answer. And it's also a correct answer, and you get the LLM to prefer this over the other. You can also hard code this, of course, but in general, LLMs are usually preference tuned for safety and helpfulness. So the Llama 2 paper had actually a pretty good section on showing how it's a trade-off. Usually you trade off accuracy with safety. So when you make an LLM safer, you lose a bit of the accuracy, but often in, if it's a public LLM like ChatGPT, you want to minimize, sensitive information leakage or it using swear words or it giving you dangerous responses and that stuff. Yeah. And it's actually quite, I would say, involved how that works, but just the overview is you still do the supervised fine-tuning that I just talked about. So it's still something you would do anyway, but then you do the preference tuning on top of that. So what you have now is you have, let's say, instruction fine-tuned in LLM, and then you use the LLM to generate responses. And there are some parameters you can tweak. There's something called a temperature parameter, where each time you use the LLM, you can actually observe that also in ChatGPT. When you use the LLM, it gives sometimes different answers, even though the query is the same. And so you collect these different answers, and then you have a human ranking them, like which one is the best, like from best to worst. And so you get these labels, and with the labels, you train a reward model. And this is another LLM, and it's exactly usually it's the same architecture as the original LLM. So you're just training a second LLM here. But that LLM is basically scoring the answers. So it's like a simpler model in a sense. It's not writing anything. It's just analyzing the responses of the other model. So here you're basically automating this ranking. And then when you rank your LLM, then you actually use that rank LLM that judges the responses of the other LLM and fine-tune the LLM based on the responses. So you can think of it as still your supervised instruction fine-tuning LLM. It generates responses, and then this reward LLM gives this a score, and you want to maximize that score, basically. So in that sense, it's like a game the LLMs are playing, where this LLM is criticizing the LLM, and the other one LLM is trying to optimize the rank, essentially, or the score. And that's how you preference tune. And this is, historically a bit expensive because you have two LLMs that you have to keep running at the same time. And if you have a very large LLM, you might not have the GPU RAM, the video RAM, to keep two models in memory. So it's more expensive. So there was actually a method called direct preference optimization, which skips that. So you are basically, there's a trick where you can just, with one LLM, do the preference tuning. So if you're interested, I implemented this also from scratch. It's a bit, a lot of code, but yeah. So Llama 3 did that, for example. But now DeepSeek, they did regular reinforcement learning. So I wouldn't say one is better than the other. There are papers showing, that this method with a separate reward model is a bit better, but the other one is faster. And so if you have more data, actually you can get more bang for the buck because you can run iterate through the data faster than with this one, it's actually better to use this one. So I wouldn't say one is better than the other. I'm just mentioning that two different ways, popular ways to do preference tuning. And there are, of course, also subcategories. So DPO is basically the original method. There's also, I don't know, KTO, TPO, and there are many flavors of that, but that's like the general idea here. Yeah, and if you want to read more about this, I have actually also articles about that where I go through this a bit more in detail. So we talked all about that, and maybe for the last 5 to 10 minutes, just a bit about the reasoning models. I promised this in the beginning, but I thought, it makes sense to go through the 3 stages before, because the reasoning models, they build on top of it. Because the reasoning models, just to skip over here, the reasoning models are actually based on technically the instruction fine-tuned model. There is one that is based on the foundation model, but that is only for research purposes. So the real one is based on the one that we just discussed, essentially, the supervised instruction fine-tuned one. And so just one step back. So everything we talked about, also if you like code, if you are into Python, it's all step-by-step coded in my book if you are interested in, learning a bit more about implementation. But this is on a single GPU or on a laptop. You can actually, I ran everything on a MacBook Mini. Everything works because it's for educational purposes. It's not, it's not costing millions of dollars, basically. That's what I'm trying to say. And so just briefly about the reasoning models. So how do they fit into this context? And so maybe one more question to you for the audience is, how do you even define reasoning model? What is a reasoning model, basically? Maybe any idea?
Model that takes some steps to get to an answer. So look at the question and then say, okay, this is step 1, this is step 2.
Yeah, I think I wanted to give some other person also a chance, because I think there was another hand, but that's a pretty good answer. But if maybe someone else also wants to say something, but otherwise,
instead of just giving one answer, it breaks it, figures out how many answers could potentially be, and like prompts itself multiple times and tries to figure out what's working, and then checks itself and keeps prompting itself until it figures out a good answer. Rather than, it's kind of like asking somebody to a question and just spit out an answer versus think about it for a little bit.
Yeah, I think that's pretty much it. I mean, different people would give different definitions. It's always like that in deep learning and AI. Everyone is redefining something, and then people get picky about what something means, and it's okay, because even with the term large language model, it's like controversial. Is it really understanding language or something? I know you can look at it in different ways, but the way people refer to reasoning models most of the time is like what you said. It's like this, they're intermediate steps, basically. Like it's like I would say it's a spectrum. There's no hard cut off. Okay, this is a reasoning model and this is not a reasoning model. But the way because even if you use GPT-4, it can reason on some tasks. I mean, what is reasoning actually? But so in that sense, when we talk specifically about these new models, they are very good at the intermediate steps. And so this is not the best model. It's just something from the DeepSeek paper that kind of illustrates what they mean by reasoning. It's essentially, if you have a question, instead of just giving you the answer at the end, it's showing you how it got to the answer, basically. So showing you the process, explaining the process. I could have maybe made a better slide here, but what I'm trying to say is, it's showing you the thought process or how it arrives at the answer. And it's almost like the difference between back in college or even in middle school when you solve a math problem, you get partial points when you get the correct. At least we got always partial points for trying to solve the problem and writing down the steps. If you only give the final number, it's it's correct, but how did you get that? Did you cheat, or what was your thought process, basically? So that's what I would say is the reasoning part about these models.
So Sebastian, was that actually a line in the response? Like, wait, there's an aha moment I can flag here.
Yep, it is actually. And this is actually pretty cool. Why it's cool is it just emerged automatically. They didn't specifically train the model to say that. And that's why they made it probably a table. They observed this interesting aha moment, basically, as an intermediate, an intermediate model produced this, basically. They were also quite surprised because they didn't teach the model to do that. It was just, something the model did.
Very cool.
That is very cool. It's also, I can tell you as a parent of a college student, it's, a lot of people think, students are trying to use it, LLMs and, all this ChatGPT to cheat. No, actually, I think, based on what I hear from my daughter and, herself for sure, they use these AI technologies and LLMs to learn. It's a great learning tool. You can
I use it myself too to still learn new things. It's I must say I never experienced that. I think I left academia in 2022 in January, before ChatGPT came out, or maybe was it the year when it came out? So luckily, I like teaching a lot, but I always hated grading, and that would have been. I was also I think 2021, the COVID semester, where everything was online, and it was really hard to make tricky questions that people can't just answer with tools. But I don't know how. Like you said, maybe it's not as bad, but yeah, I don't know. But then it's the same with pocket calculators, right? I mean, it's like, why do I have to do everything in my head if in real life I can actually use that calculator? Like why don't you learn the real world? And so you can real problems, so you move on to more difficult problems. Basically, you can't, just type in. You still, make the problem more challenging, basically.
Well, actually, specific to it, actually explaining the steps. Like my daughter likes it to learn how to do something. She doesn't want the answer. She wants help on, how did you arrive here, right? So some of the questions are difficult to get to. A lot of the students are not using it to try to cheat, but as a professor, they're struggling with a problem, or have a better insight on how to solve a problem, maybe different ways of solving it, and it's stepping through. The more it can step through and give you the details of how it arrived at the answer, the better learning opportunity. I think it's really valuable. And OpenAI is a little bit more guarded now. They've actually, I've heard, they've limited what they expose because they don't want you to really know their.
The reasoning models. Yeah.
So I appreciate R1.
the
not being as guarded.
Yeah, no, like what you said is exactly also right. It's also a private tutor, basically. Instead of, before you had to ask maybe teachers, but teachers were not always available, or you had to ask a friend for explanations. Now you have this thing 24/7 that you can use, which is, I do this myself a lot. I use LLMs every day for certain things,
Actually,
also just to double check
the other day. Sorry, I was going to say I used Perplexity just today to give me advice on a new gaming PC that had a couple of conditions, and it was going through the reasoning because it was using R1, and it was going through the reasoning. It's like, okay, I got 10 reviews, and these are the different reviews. Oh wait, the user said I wanted to have a quiet PC, so this one is not applicable. Oh, it had to be a medium range, so this was using an i5, so we're going to drop that one. It was funny to see the different steps that it took. So, okay, this is
correctly. That's it's almost like this one here, right? The wait.
Right, exactly.
There was actually a paper just January 31st. It was called S1 something, where they did only instruction fine-tuning, but they had weight tokens in the data set, and they observed that this actually improves reasoning. There's something about weight. They had different words that were not quite as good, but weight was for some reason, the magic word there. The paper is called something with S1. You can find it later and share that. It just came out like a few days ago. Anyways, so one thing also about reasoning models, though, is what are reasoning models good and bad at? So actually, reasoning models are great for certain things, but I wouldn't use them for everything because they also have some downsides. So what they're good at is, of course, more complicated queries like riddles, math proofs, and code tasks, and so forth. Like where you need like some chain of thought reasoning. So that's like a number of steps, like multi-step problems, basically. And in general, just these complex decision-making tasks, like the gaming PC, for example. What they're not so good at is like being cheap and fast. So usually these models are much slower. And there's certain reasons why they're slower. But so that is one thing where you don't want to use a reasoning model. Like if you think back of 01, when it came out, it was like 10 times slower than 4.0, for example, and so it's also costing more money to run those models. So it's not for everything, and they're also on benchmarks. They are actually worse on knowledge-based tasks where you have like a short answer. So if you ask like historic facts, they get them more often wrong than non-reasoning models. And I guess it's just LLMs have a limited capacity, like a number of parameters, and if you teach it something new, it kind of tends to forget the old things, and it's just like a trade-off always. And for simple tasks, you can also sometimes see it makes mistakes because it's overthinking, and that's to some degree also true with humans. If you have an intuition, sometimes it's right. If you try to think about it more, sometimes you introduce errors unnecessarily. Often on difficult.
You're overthinking it. When you answer incorrectly. How many times have you heard you're overthinking it?
Yeah, exactly. Yeah, yeah. So yeah, and so there are pros and cons, like what reasoning models are good for and what they're not good for. And yeah, just to wrap up how everything relates to what we just talked about. There are 4 main ways to build and improve reasoning models. So there's one way, it's just increasing inference compute, and that essentially means spending more time on producing the output. Without any training, you can take any LLM out there, not trained for reasoning. Any LLM could be the first generation of GPT, and you can improve it by spending more time on the compute. It's like the analogy is for humans on harder tasks to think longer. And how you can do that is in multiple ways. The classic one is you can, to the prompt, no, it's not necessary anymore, but early generation ChatGPT, what you could do is you can say, think step by step. So if you have a question and you say, think step by step, it will automatically create a longer response. And why is this increasing the compute? So compute is also a weird jargon term. I use it now all the time, but it means computational resources. At some point, compute is like the fancy term everyone uses. With that, I mean computational resources. So why is it using more computational resources? So if you generate an answer, and the answer is twice as long now, it's using twice as much resources, because the way LLMs generate text is 1 word at a time. And so instead of 10 tokens, output tokens, you have maybe 20 tokens. So it's twice as expensive. So that's one very simple way to spend more compute, like more computational resources. Another way that also a lot of LLMs do behind the scenes, I think it's not known, it's not publicly disclosed, but I think all the GPT-4 models might be doing something like that. So this was a paper by Google that came out in August. And so what you can do is you can actually do some better sampling there. So instead of having the LLM just generate 1 response, you can have the LLM generate multiple responses, for example, here on the left-hand side, and then you pick the best one. How do you pick? I mean, if it's just a number, you can go maybe by majority vote, but you can also, here they do train a separate model, a verifier, that just looks at the responses. It's usually a simpler model, and it just picks the best answer. There are also other search algorithms, beam search, where you generate different responses, look ahead search and so forth. And but the idea is essentially you make it's more expensive to do that, but you spend more effort on generating outputs. And I strongly suspect O1 is doing that. Not only that, but it's part of O1. I strongly suspect that. What's interesting though is DeepSeek is not doing that. So DeepSeek R1, according to the paper, they achieve the performance in the benchmarks just based on training. They don't do anything like that. And this is why DeepSeek is also so much cheaper. That one is of course a mixture of experts, but back when GPT-4 came out, it was also rumored to be a mixture of experts. So it can't be only due to that. And I think O1 is so much more expensive because they do inference compute scaling, basically. But it's just speculating. I mean, they don't share the details. But this is something you can use for any LLM. And what's actually cool is if you do that on top of DeepSeek, you would get even a better DeepSeek model. They're not doing it right now, but maybe in the app one day, or maybe they do that in the app. But they didn't. They said in the paper specifically that they didn't do that for the benchmarks in the paper. Yeah. So, but yeah, this is. But in APIs, I believe this is pretty common in ChatGPT throughout the model families. But yeah, maybe I'm wrong one day when they disclose that. But yeah, yeah, you had a question?
Yeah, I mean, you could conceivably, like, we could take the R1 model, since it's open source, and build this on top of us. Like companies can do that, right?
Yeah, 100%. Yeah. So I think this is coming. Someone will do that and improve DeepSeek a bit more with these techniques. I mean, these are described here. It was in August 2024 by Google. It was a Google paper, but I mean, this is not new knowledge. They were just summarizing that basically. Like it was. I mean, I think they proposed some unique techniques. They're not shown on the slide here, but this is like something people have been probably doing for years. I think in the DeepSeek paper they didn't do it for simplicity, just to show the pure training results. But then also, it's like a more like an application thing that you do later in the deployment, and also to keep it cheap. Because I think they wanted to focus on keeping the price low for the token user, for the dollars per token. Yeah. But yeah, what did DeepSeek do then? So what they did is, what they focused on is on training. And by the way, I mentioned O1 is doing it, but I think O1 is also training. What I believe is speculation, but I believe O1 is a simpler model than DeepSeek, a smaller model, where they did do training, but less training than DeepSeek, but they compensated for that using this scaling, if that makes sense. So basically they had both training and the scaling, but the focus was more on the scaling, the inference time scaling, which makes it more expensive, where DeepSeek focused only on the training, but training a bigger base model, which is more powerful, essentially. Yeah, and so what they did is they did this reinforcement learning, which is quite similar to what I've shown you. If I go back, it's basically similar to this here, where you have this reward model. So that's why I was spending a few slides on this. So they have this other LLM, the reward model. And actually, in certain cases, it's not even an LLM. So what they have is, they have accuracy rewards for rule-based things. So they had math verifier. So they just used, you know, I don't know exactly what they used, but you can use Wolfram Alpha for math questions to check if the answer is correct. And you can use for code, lead code compilers. You can run the generated code through, let's say, the lead code compiler or some other tool to see if the code works, basically, and gives the correct answer. And they had a format reward just to check if the model generates these think tags, just to that it adheres to the format, basically. And for that, I think they used an LLM. But overall, just doing that, only the reinforcement learning, the LLM learned based on, is this correct or not? Nothing more. The LLM learned to generate this whole reasoning trace. And this was quite fascinating. They were the first to show that you don't need this as a template. You only need the question and the correct answer, and the LLM will learn this step-by-step thinking, basically, just by saying what's your answer is correct or incorrect, basically, which is very fascinating. No one has shown that before. Yeah. And yeah, so that was one experiment in the paper. And this is the DeepSeek R10 model. It's not their best model, by the way. It's just, I think they did that for research purposes. Then they had a different model. They used both reinforcement learning, but also the supervised instruction fine-tuning. So if I go back for a few moments, I mentioned before, here you start with the supervised fine-tuning. When I showed you this R10, they didn't do that. They just jumped ahead here. They did this step, but they didn't use the fine-tuned LLM. They used the pre-trained LLM. Now they're using the fine-tuned one. So they did that essentially for research purposes to see whether the thinking emerges as like a result of the fine-tuning or instruction fine-tuning or the RL. So they just did the RL and they said, oh, the reasoning emerges from the RL actually. But then to get a better model, they did the regular steps basically, because you get better performance if you do both. I will show you in a few moments. Yeah, so now this is the regular R1 model, not the 0 model. And just to compare those, so they had this RL only model where they only did a reinforcement learning, and then the R1 model, which has supervised fine-tuning plus reinforcement learning. And you can see the larger numbers are better here. You can see it's quite a bit better than the other model. They didn't have a table where they had both models, so I just added this here at the bottom because the numbers were in the paper, just in different tables. Yeah, and you can see the model is on most tasks, except this one here, it is better. So this task is actually interesting. This is general knowledge. It's biology and chemistry knowledge, and this is code, and this is math. So you can basically say almost the model gets worse at chemistry and biology for some reason. I don't know why. Yeah. Yeah, and then they had a third class of models. It's just the fourth way here. It's a third class of models, and these are the distilled models. And here they fine-tuned smaller models, the Gwen 2.5 and Llama 3. That's why I had them earlier in the slides. And for that, they used that instruction fine-tuning, only instruction fine-tuning, nothing else. So one moment, I do think I have a, maybe we jump ahead here. I have, yeah, made a figure. There's like a little mistake in here. This arrow should actually, sorry, this was correct, but then there shouldn't be a connection. Sorry, I'm just correcting it here on the fly. Then I will talk you through this. It's a bit ugly, but I think you know what I mean. So what they did is essentially they had these multiple models. They had DeepSeek version 3 as the base model, the pre-trained model, and then they developed this R10 model just with pure reinforcement learning. And then they had that model generate the supervised instruction fine-tuning data. So they used, again, the pre-trained model, this SFT data, with some more SFT data, and then they came up with this R1 model. Yeah.
You're not showing your screen.
So did my, oh, because I exited briefly my slideshow to correct my slides. I'm sorry. Thanks for letting me know. Yeah. So yeah, I was just adding this arrow here at the top, which was missing basically. It looks a bit ugly here because I just did this on the fly, but yeah. So just to yeah, summarize, so they had this version 3 model, the base model, which they developed back in December. It's just a pre-trained model. It's no reasoning model. It's just pre-trained. And then they had the RL, and from the RL they got the R10 model, which has some reasoning capabilities. And then they used that model to generate this instruction fine-tuning data. And so then they went back, used again that pre-trained model together with this data, so going down this path, They did some more RL, and they did some more instruction fine-tuning. So they generated some chain of thought data, and they generated some general knowledge data with the original model. And then they developed based on that, so multiple RL and SFT steps, they developed this R1 model. And then separate from everything, they just used this data set, instruction fine-tuned data set, and then they distilled Llama 3 and Gwen and came up with these models, basically. So there are 3 types of DeepSeek models, basically. Yeah, and what was fascinating is that pure RL, this one can already reason. This one is the best reasoning model because it has more stages. And it's also fascinating, just with instruction fine-tuning, you can still get pretty good reasoning models, the distilled ones. So going back a few slides. So they were actually not terrible. So these are the distilled models. And compared to O1 Mini, for example, it's doing pretty well, actually. It's actually better than O1 Mini, basically. Although I must say O1 Mini is probably also a distilled model. We don't know, but I suspect it is. Yeah. And compared to R1, yeah, they are weaker, much weaker, but in certain categories, they are actually not too bad. It's a 94, it's a 97. It's not far away, given that it's a much smaller model. Yeah, I think, with that, I talked a lot. The slides are, I think, in the chat. There's the PDF, and I'm probably more active than I should be on social media. If you are on there, I usually post research papers or these types of things. And yeah, if you want to reach out, I have my contact here on my website, basically. So yeah, with that, I hope this was interesting. I know it was maybe very technical, but it's what I like talking about. So I hope you like this and found it at least at some parts useful. And if you have any questions, I'm happy to chat. I think a few more minutes. I mean, if you are still not bored and want to hear more about LLMs, let me know.
It was really interesting to see the different parts and how they work together to create the AI, for lack of a better word. Thank you.
Yeah.
My name is Donna. I have a real quick question.
Mm-hmm.
I was working with Gemini, not working, just sitting there watching a movie, Dune, and I was losing track of the characters. So I was asking Gemini, okay, pause the main character, who's the sister, who's his wife, who's his lover, and it was trying to convince me that he had 3 kids and his sister was his kid. So obviously it was, and I called it out. I said, wait, you just told me that was his sister. How can that be his kid? And it came back and it said, oh, you're right. I got that wrong. I'm so sorry. I'm still learning. Where does it occur? Where does the fix for hallucination or fabrication come in? Is that retraining?
That's a very good question. So honestly, I never used the Gemini models because I had similar experiences with early generation models, and maybe it's better now. It depends for you also which model. They have a whole selection, but yeah, like what you said is like sounds pretty bad. Actually, I saw the movie, and yeah, this is like it's not a good LLM in this case. So it's tricky. It's a good question. Where does it come in? So the thing is, in pre-training, it gets all the knowledge from the internet, or part of the data set is the internet. So there could be wrong stuff in there, but maybe on Reddit someone had wrong answers. It could have learned from there. But let's say there are no mistakes in that data set. It can still make these mistakes, these hallucinations, because you don't want the LLM to literally memorize the data set. Actually, you could do that. If I go back to an earlier slide, if you train the LLM long enough, it will at some point memorize. So it will be more likely generating exactly verbatim what it has seen on the internet or in books or something like that. I don't know. 1 second, I was somewhere here. Yeah, this slide. So you can see, like, so this is like, it's called loss, but when it goes to 0, this is perfect memorization. And the longer you train it, you could technically get rid of this hallucination. I mean, not getting rid of it, but like increasing just the verbatim responses. But that's also not good, because then the LLM would only copy paste what it has seen in the data set. So it's like a slippery slope, because you want the LLM to memorize certain things, like what you said, like this query should get this correct. Or if you ask historical numbers or facts, you don't want it to make up new numbers. You want literally that it uses the correct numbers for historical dates. But at the same time, you don't want it to just copy paste what's on the internet, because that would be plagiarism or copyright infringement. I think they have some lawsuits because they do sometimes copy verbatim. But yeah, and so one part, like you correctly said, is during the pre-training, you can control that to some extent. But then the other one is when you deploy the LLM, there is, I'm not showing this in these slides because it's like a lot of code, but there is when you sample the outputs, so I don't think I have a slide on that, but so going back to maybe this slide. So there's this input layer, and the input layer has the same size as the vocabulary. So all the words that the LLM knows, in the case of GPT-2, it's about 50,000. I think GPT-4 has 100,000 different words that it can pull from. And if it can also generate unknown words by concatenating different characters together. So, but I'm trying to say is this layer is a matrix multiplication or an embedding layer that creates this internal representation, but at some point it has to go back to the text. So, and that happens in the last layer. And this last layer has the same size also as the vocabulary. So let's say 50,000 words. And so for each, I'm not showing it here, but for each word that the LLM generates, it gets actually a vector of 50,000 words, all the words in vocabulary. And each vector has a probability. So let's say if I have this input text, every effort moves, and then it has all the possible 50,000 words. Each one has a probability. Every effort moves, let's say, bridges or cars. The probability would be relatively low because it's a rare word in that context. But the probability for you might be 80%. So it would pick the most likely word as the next word. And so it's generating one word at a time by picking the most likely word of all the words that it can pick. And during the application layer, there's a parameter, it's called the temperature. You can tweak that, you can change the probability distribution, and you can sample randomly from that to some degree. So you can kind of like control the degree of randomness by having the LLM sometimes pick words that are not the ones with the highest probability. And because if you always pick the highest probability ones, you will likely regenerate just the training data set. But if you add some variation, you don't pick an unlikely word, but you pick a likely word that is maybe not the most likely one, but very likely one, then you can add this variation. And yeah, if you get this parameter, if you set it too much randomness, then you get more hallucination. And if you set it too low, then you get more memorization. And it's a slippery slope, basically. Yeah, so there's no perfect solution right now where you always will get some hallucination at some point. It's just trying to get this down, but I think you can't really perfectly address this. And in this case, the LLM you used, it's a mix between maybe bad settings, but also smaller LLMs, they make more mistakes, basically. Yeah. So it's likely a smaller, cheaper LLM too. Yeah. Oops, long answer, but I hope this kind of answers it. Yeah.
It does. Thank you.
Mm-hmm.
So if you own the data that your LLM is trained on, you want that predictability to be as high as possible, because you're okay with regenerating data.
Mm-hmm.
So I think that's called the temperature or something.
Yep, exactly. The temperature. Yep, the temperature.
Okay.
Yeah. So it is. There's like a softmax function, and I don't know why they call it temperature, but it's essentially just a rescaling the probability distribution, basically.
Right. Yeah, we use a bot at work that we've trained on our documentation from IT. So when we have a question about like how do you do a certain thing, it actually goes out and retrieves the document. But we wanted to respond the same way every single time that we asked a similar question.
Mm-hmm.
So that temperature should be set to like X0.
Zero, basically. Yep,
yeah.
Yep.
Okay. Yeah, I always confused if it's 100 or a 0. So.
I think the highest would be a 1 that you can set. You can set it. I know you can set it higher for sure. You can set 100 on. You can, I think, go infinite. Yeah. I'm just trying to see. I should have a figure on that. Yeah. So let me see if I can share my browser tab. Sharing the whole window. Let me just. It's an infinite mirror here. Here we go. Yeah. Yeah. So here, for example, this is like a chapter from a book, basically, but here, that is basically what happens when you change the temperature. So the temperature of 1 is like the default. And so I'm just assuming a very small subset of the vocabulary, like the different words. If you have every effort moves you, so if our input is every effort moves you, what is the next word it should generate? And so you get the probability distribution in blue with temperature 1. The most likely word is here forward.
Gotcha.
Every effort moves you forward. It's a very almost, yeah, it's a 0 probability for effort, because it wouldn't make sense to say every effort moves you effort. That would be a mistake. And so you have this distribution here, but you can rescale that. So if you set the temperature lower, the probability becomes higher here. So it's more likely picking this forward one. If you set it to 5, you make it lower, so it becomes more random. So the other ones also can get picked. So before effort was close to 0, now it's a small chance. It's a, let's say, zero, maybe a 5, if this is 10%, maybe 5% chance to pick effort. So once in a while, it will pick a wrong word then. And so you have basically, so the temperature is a scaling factor here, but when you sample, you sample from a distribution. So you don't always pick the highest probability, you pick it proportionally to the distribution, basically. So you pick, in this case, when you have the temperature of 0.1, yeah, you will pick almost with 100% always this token, but otherwise with temperature 1, you will only pick it with 60%. So then the model can, 60% of the time it creates every effort moves you forward, 40% of the time it creates every effort moves you toward, which is not wrong either. You know, it's yeah, and that way you can control it basically. Yeah, hopefully that answers it even better.
So the higher the temperature, the higher the chance that Paul's sister is actually his daughter.
Yeah.
That's great.
What surprised me was that it kept apologizing, because I would ask it a different question, then I would go back to the original and it would give me bad data, and then it would say, "Oh, you're right. No, that it can't happen that way."
Yeah, they're very good at apologizing. I had it with code as well, that I was asking a coding question. I was like, no, that's wrong. Oh yeah, you're right. They give me the same answer again.
The customer's always right, right?
I wish they had a way of, when they give answers, what's missing, I think, is they're always so sure, right? Like when if I go to Ron and I ask Ron a specific question, maybe it's a difficult question, Ron always knows the answer, but let's pretend like he doesn't, and he has a guess on what it is. When he responds to that, he's not going to be like, "Oh, no, Tolga, the answer to that is you plug it right there and you move it. That's what you do." But if he's not sure, he'd be like, "Well, probably, you probably want to move it. I mean, have you tried that?" He'd be less certain about how he gives the answer.
Yeah.
I think that's still missing. That needs to be figured out when the GPTs are actually giving the answer. They need to be able to. There needs to be a gauge of how certain they are on the answer, and respond with a way of gauging that. I mean, if it was the voice model, it'll be easier to do, right? You can definitely make it in your voice tone. Text it a little bit harder, but you need to figure that out. I think that's kind of.
I think this is exactly right, where right now it's only trained on the correct responses, but I mean, it's implicitly trained on the wrong responses because it gets a penalty if it itself makes the wrong response. But there was actually an interesting paper to that point that came out last year, where they proposed something called journey learning, where they also on purpose include the incorrect answers. So traditionally, you only correct, as in reasoning models, you only provide instruction fine-tuning the correct chain of thought. Only this one, but they proposed, hey, let's also include the wrong answers someone could make, and they found this actually helps. It maybe doesn't help with the self-correcting necessarily like that, but it in general helped with the accuracy. I mean, like a little trick where they included wrong responses as well, in addition to the correct response. So it's not the perfect solution, but I just found that interesting in terms of what you just said, basically, like how do you get the LLM to recognize when it's wrong, basically,
Yeah, or just not, if it's not certain, like it has to get one answer. But if it can ascertain somehow that there were multiple paths, right? It chose one because of the temperature or whatnot, but there was a lot of answers close to each other, right? Even with the randomness, there's still lots of possibilities, rather than one that's sticking out.
And this is actually where this inference compute comes in, where, like you exactly said, there are multiple answers sometimes, and then you can actually take advantage of that, but you need another model basically that then picks the correct answer, basically. But it's exactly like trying to address it, but also, like you said, it makes it more expensive because you have multiple answers now, multiple temperatures, and then you have to generate multiple answers, and it's like a slippery slope where you can either spend your time on training the model more. It's like a one-time investment, and then you can just use it cheaper, or you save some money during training and do only this, or you do both. It's like people are trying to figure out what is the best ratio there, because the more customers you have, the more expensive this approach is, because you pay extra for each customer, where pre-training is like a fixed cost, basically. It's an interesting field. It's so much happening all the time. It's but I was just telling you here is maybe outdated in 2 months. There's some new paradigm. It's evolving so quickly, which is exciting, but it's interesting.
So Sean raised his hand as well, so I wanted to interrupt just to let everyone know that.
Yeah, so if there are any more questions, I think you're muted, Sean, maybe.
Yeah, I had audio problems earlier. Still having an
Okay.
okay.
Sorry, Sean, if you were talking earlier and I never responded. I think we never heard you, unfortunately.
Yeah, no, I think he still has microphone problems. So
Oh.
I don't know if you can put it in the chat, Sean. Question.
All right. Well, you can always post your questions maybe in the comments of the YouTube video that we're going to post here. So I really appreciate having you, Sebastian. This is a fantastic topic, and maybe one day in a few months you can come visit us again, and maybe the topic will be completely different. I mean, same topic, but the material will be different. It changes so often, it never gets boring.
Yeah, it never gets boring. That's true. Yeah.
Oh, there we go. Sans was posted in the chat. How do we make sure that we don't confuse correctness with temperature with truth?
Yeah, I mean, I don't know if I. So I think the thing is also the temperature only kind of addresses the problem of making up new things that were not already there in the training data, but it doesn't mean what the training data contains is correct. So that's a separate issue where you could still have zero temperature. It produces perfectly the training data, but if your training data has incorrect facts, historical facts, it will get them wrong. So it's like, yeah, the temperature is not everything here. It's like, that's also coming back to why they spend, or companies spend so much work on this part, like the data filtering and everything, and synthesizing data and this multi-stage training. But particularly the filtering. I mean, there are major stages nowadays where they train LLM to remove low quality data and have verifiers and even humans discarding information. So, and then the data mixing, and I think they're weighing like books, academic books, papers more highly than, let's say, Reddit posts or blog articles, where yeah, it's really getting that high quality data also at the end. There are a lot of these tweaks, but they're all workarounds. You are just hoping these are more correct, but there's no guarantee. So yeah, so in the end, unsolved problem. That is achieved here also in the preference tuning, but that assumes that the humans who are ranking those have knowledge, and that's also not always true. There's a lot of ifs, a lot of assumptions. Yeah.
Yeah, going back to the example with the laptop or the computer that I was researching, like it's based on reviews, and you never know if the reviews are based on actual testing or that they're sponsored by somebody, or yeah.
Yeah.
Or the Dune example that you,
yeah.
The Dune example was like a good one. Yeah.
Yeah. The last thing, just also about that is when they used, or when they did the reinforcement learning for the reasoning model, they used verifiable answers. So where they had actually a calculator, let's say, program that evaluated so you can generate these data sets, right? You can use, I don't know, Python code or any language. You can say 2 + 2, and then the answer is 4, basically, where you can verify it deterministically. And the same, like with the lead code compiler, you can actually run the code and double check. So in that case, part of it was actually using these verifies where you do have certainty, but still that's not enough to always, come up with the correct answers. It's increasing the probability, but it's never 100%. You try to get to 100%, but it's even the best LLM on simple questions is always 99.9. It's never 100% because of how the sampling works and stuff. Yeah, well, thanks for inviting me, and I actually enjoyed this quite a bit, so it was quite fun.
Thank you. It was a great talk.
I really appreciate you being here and explaining this to us, and it's a fantastic topic, and it's going to continue to be that way for a long time, I feel like. All right, appreciate all of you. Have a great night.
Bye, everyone.
Thanks, everybody.
Yep, you too. Bye, everyone.